Now that we've talked about both resistors and capacitors in circuits, let's talk about resistors and capacitors in the same circuit. Such a circuit where there's both resistors and capacitors is known as an RC circuit. R for resistance, C for capacitance. Now, this is a simple diagram that can depict what one of these RC circuits might look like, where you have some voltage source with a resistor or capacitor, and then often there's a switch to turn it on to time it. Now here's what makes this so unique. Without a resistor, you just hook up a capacitor to a battery. The capacitor charges up in such little time that time is practically not a question. The capacitor charges up very, very, very fast. Now, if you add a resistor to the circuit, that slows down the current, and it slows down the current enough that you can actually measure how quickly a capacitor will charge. Such circuits are really good for timed charges, such as timers, pacemakers, cars' turn signals, wipers, etc. And by the end of this video, I'll show you how that is done. Okay, so here's the idea. You have a resistor and a capacitor in a circuit with a battery, but the switch is open, so no current is flowing. As soon as you close that circuit, then the voltage inside of your capacitor starts to increase rapidly. But as the capacitor fills up more and more and more with charge, it's going to slow down that current until it approaches the original EMF of the battery itself. This is an exponential function, and so you'll see in the very next slide that the way that you calculate the voltage within the capacitor is an exponential function. So what's happening with the current at the same time? As soon as you close the switch, all of a sudden you have a very high current driven by the EMF. But then as the charge within the capacitor increases, the current is going to decrease until you get further and further and further along in time. More and more charge builds up on the capacitor. It's going to slow the current exponentially. Now we have a number in here, T equals RC. RC is just the product of the resistance and the capacitance. Now this is a very important number mathematically. The time RC is the time it takes to reach 63% of your maximum possible voltage. It's a statistically important number, and so this is a very important value. So we're going to give this value a name. This is our time constant, and we're going to use the Greek letter tau, T-A-U. Tau, or the time constant, is just going to be the product of resistance times capacitance. So time constant is a very important property that describes each RC circuit. Now, how do we actually calculate the voltage in a capacitor? The voltage of a capacitance is going to equal the EMF times the quantity 1 minus e to the minus t over RC. RC, of course, being your time constant, t being the amount of time that has passed. This is the exponential function that matches this middle graph. Now, the amount of charge that's on a capacitor is actually going to follow the exact same curve, except it's going to be Q equals Q0, meaning the maximum amount of charge on a capacitor, times 1 minus e to the minus t over RC. Okay, so charging a capacitor in an RC circuit is great, but what's awesome about RC circuits is that if you can find a way to remove the voltage source and leave a charged capacitor in an RC circuit, then the capacitor itself becomes a battery. A very short-lived battery, because when the switch is closed, it generates a current, and the charge is dissipated rather quickly. But all the same, it's very useful, and you'll see in a second why. So if you have a situation like this here, where you have a capacitor and a charged capacitor and a resistor with an open circuit, the capacitor is charged to V0. Then as soon as you close the circuit, that voltage is going to drive a current, but the voltage is going to decrease because you're losing charge. And it's going to decrease in an exponential function yet again. And so we find that the charge on the capacitor will decrease exponentially, that Q is equal to Q0, the maximum charge, times e to the minus t over RC. And likewise, your voltage in a capacitor is going to be, the initial voltage times e to the negative t over RC as well. Okay, so notice the difference. When you're charging, the function is going to be 1 minus e to the negative t over RC. When you're discharging, it's just e to the negative t over RC. So here's what's cool about this. If you could somehow switch from one way to another, having a voltage source to not having a voltage source, then you can alternate between charging a capacitor and discharging a capacitor. Charging, discharging. So you can get a graph that looks like this. So we start off with the situation on the left where you have a voltage source. You're going to charge your capacitor up to a certain point. Once you reach that set point, a switch flips, it removes the EMF, and you end up with this situation over here, in which case you're discharging the RC circuit. It starts to discharge, it hits a set value, the switch flips again, reintroduces the EMF, charges up your capacitor. Then once you hit that value, it switch flips again, discharge again. Hit the value, switch, switch, and you can see you end up with an oscillating pattern that is very consistent in time. The amount of time between each of these points is very consistent. I can't draw it consistently on my screen, but you get the idea. And so this works very well as a timer. So let's say you have a pacemaker. You have it's set to a battery. The RC circuit within a pacemaker will charge up with the battery until it reaches a particular voltage. Once it reaches that voltage, a switch in there flips and the capacitor is discharged, and that discharge causes the heart to contract, thus pushing all the blood through the body. Then once it's discharged enough, the switch flips, the capacitor charges again. Hit that maximum voltage, it switches again, induce a current into the heart, causing the heart to pump. And so you end up with a very steady beating heart. And there are lots of other applications for an RC circuit like this. Windshield wipers in your car. Ever wonder how the car knows how much time is in between each wipe? Well, it's an RC circuit. The time constant is determined by the resistance times the capacitance. There's a dial on your wiper gauge in your car where if you turn the dial, that's effectively changing the resistance in the RC circuit. And by changing the resistance, you change the time constant, and thus you change the speed of the wipers. And there's a multitude of different appliances you can use with RC circuits.